Okay, so what we have to remember now is, so I'm going to take right now my sample sizes are going to be, we'll do size 5. Okay. And actually, we're going to do it from a skewed population. Yeah, we're still, no, it didn't, uniform. I don't know. It said skewed, but it sure wasn't skewed. There's my skewed population. Okay. I'm going to animate that size 5. So just a refresher of what we're doing. I had a sample of size 5. And what we're going to do is we're going to work with sample means. So the mean of those 5 individuals that were in my sample, I'm pointing at them. You can't see that. That's the only thing I don't like about now. Okay. I have no way of pointing. Anyway, that blue dot down at the bottom. And yes, I remember doing this now because I had the same exact issue. Okay. So there's my blue dot. Okay. If I did if I did 10,000 of those, okay, we can see that I have if I look at the blue distribution, it's out there at 2, and then it rolls out to whatever number about halfway. So that's probably about 16. Okay. However, if I increase my sample size, if I double it to size 10 and I give myself 10,000, if you look at the blue distribution again, you can see that my variability has decreased. And again, because even though my sample has some really large numbers in it, okay, out there, I just erased some of them. We'll get you back. Okay. Out here. Okay. So even though my sample may have a number that's out there, because of my sample size, I'm able to defuse that really large number, and therefore my variability won't be as large. Okay, here's a to then continue on to what we're after. Okay, and I didn't work with this yesterday at all, and I wish I wish there was some way for me to laser point on this. Okay, if you look in the upper left hand corner, as far as it gives me the summary statistics of my original parent population, it had a mean of 8.13. Okay. If you look at the mean of my distribution, it had a mean of 8.11. So what we find is the mean of my sample and the mean of my population, if I have enough, okay, the means are actually going to end up being the same. The only thing that happens though is my distribution and my standard deviation is 6.28 in my parent population, but it's only 1.96 in my distribution. So therefore, that's what we mean. When we go and start doing calculations, we're still going to do normal calculations. But what we have to grasp is, because I'm working with a sample, the variability is going to decrease. So I have to make adjustments to my standard deviation in order to make those calculations. Okay. So we kind of touched on this last time. I jumped the gun on taking notes. So if we jump back out to our notes, so I guess to finish this up here, obviously we're going to expect my variability to decrease. So the range is going to get smaller. I went ahead on number 15. You're supposed to go in and draw the official mean for that entire population of 200 is 561 million. So the goal was to go back here, and we drew a line at 561 in that dot plot. We drew a line at 561 at this dot plot, and we drew a line at 561 in that dot plot. Okay, so we could see then where the actual mean was. So again, my judgment sample was poor because it likely included some of the bigger movies, more of the bigger movies. So that's why that we had those samples out to the right there. And then as we get to more randomness, we see that we didn't have that problem. And because we have the sample size of 5 here, my has some variability issues for that. And that's why we have the skewness there. Okay. Anyway, 16 and 17 is what you had to finish up answering there. So, again, I thank you for those that jumped on early, like I asked you to do, so we could finish that up. And we're going to call that finished. That is an assignment, so we need to get it done and turn that in for a grade. So we're going to head off into our notes and see where we're at here. So when we go back, so now just to continue on to what we were doing there, we talked about previously. So the mean of my sampling distribution here is going to be equal to the population mean here. So that's what we should discover. Actually, we're on that internet site for that. So I also said then that my standard deviation needs to be adjusted because my variability decreases in my sampling distribution. So this is our adjustment. We're going to take that population standard deviation and we're going to divide it by the square root of n. Okay, when we go through and check this, we're going to have the checks that we have as far as normality can be assumed. We're not getting our 3 checks today, but normality can be assumed, or it's approximately normal because either one of 3 things. If my population is normal to begin with, I'm good. I can just go ahead and make that normal calculation on my sample. If n is sufficiently large, and it's sufficiently large when n is greater than 30, I'm afraid my pen's going to die on me. And if I'm dealing with actual data, then I can use a histogram or a box plot and show that it is symmetric. Okay. So that means that we can go ahead and have a z-score, and we can go ahead and make those normal calculations as we always do. The only difference is that I have a specific sample mean that we'll be going after. I turned it off. Okay, we have that specific sample mean, we have the mean of the population, and then here again is my adjustment for the standard deviation because it's going to get smaller. So we divide by the square root of n. So that means the larger my sample is, the smaller my standard deviation is going to get to, because the larger n is, the larger my denominator will be. And so I'm trying to break that into bigger chunks. So that means it's going to be smaller. All right, so here is example 2. I am recording this, aren't I? Yes. All right. I feel like we have some we're low on attendance today, but maybe that's just I don't know. I'm babbling. General Mills sells 18-ounce boxes of cereal. Let X denote the actual amount of cereal in a cereal box. Suppose that X is normally distributed. So with a mean of 18.03 and a standard deviation of 0.05. So they gave me X. So these are population things. So we just have to recognize that they gave me a population mean and a population standard deviation because of the variables that we used here. Okay. What proportion of boxes will contain less than 18 ounces of cereal? So here's where we're trying to figure out, or if I'm going to give you everything, we know what is the likelihood that X is less than 18 ounces. So they defined what X was. Okay, so we don't have to define the variable. But this is a normal calculation, so we have to remember that we need a probability statement and we need a curve. Okay, 18.03 is here in the middle. Here's 18. I'm trying to figure out what portion is going to be underweight boxes of cereal. So if we're going to do this, 18 is the observed value, 18.03 is the expected value, and we're going to divide by the standard deviation, which is 0.05. And that means that we're going to roll over and get a negative 0.6. And then if we went to my table and looked that up, that's going to be a 0.2743. Okay. Again, if you wanted to, this is a spot where you could, I'll just write it in here. You're welcome to use your calculator. For those of you that appreciate the normal calculation in your calculator, that's what we would need to show. And just remember, if we're going to do this, that means we have to have our calculator speak. So that means this is the lower boundary, this is the upper boundary, this is my mean, and this is my standard deviation. All right. A case consists of 24 boxes of cereal. So now what happens is we have a sample of 24. Can we assume the sampling distribution is approximately normal? Now, so now we're going to go back up to this. To be approximately normal, it has to meet one of these 3 criteria. And because it said X is normally distributed right there, that means that my sampling distribution will also be normal. Sampling distribution will be approximately normal. And again, the key is we got that approximately in there, okay? Because we can't guarantee it's normal. Because population was normally distributed. I need an N there, not an M. So, what is the probability that a mean amount of cereal boxes the mean amount of cereal per box in the case is less than 18? So now what we're going to do is we're going to do an average weight of all boxes in that case. So now we're working with that sampling distribution instead. So the thing that's going to change in this, so in reality, all of this stuff, okay, this stuff here is going to be the same for down here, those two things, but now we're going to have a standard deviation for my sampling distribution. So I'm going to have the standard deviation of x bar. So we know from above that that standard deviation is equal to, we're going to adjust the standard deviation by dividing by the square root of n. So my standard deviation was 0.05. I now have a case of 24, so that's my sample size. And so when we divide that, my standard deviation now, because we're dealing with samples, is going to be 0.0102. Okay, so if we go ahead and find that z-score, so now we're still gonna have 18 minus 18.03. So the observed minus the expected is still the same. The only difference is I'm going to divide by 0.0102, and that's going to be equal to a negative 2.94. And again, we expect, since the variability goes smaller, seeing a mean of 18 is going to be much more rare, 0.0016. Okay. And again, I'll write in that normal calculation, that normal CDF. Again, it's going to look very much the same. Actually, I'm going to cheat. I get tired of writing 1E99. We'll go with 18. We got 18.03, and then we have 0.0102. Now, the thing is, though, we have to pay attention to. This is still my lower boundary. This is still my upper boundary. However, this is no longer the mean, because that's a population mean. It's actually the mean of my sampling distribution. And this is the standard deviation of my sampling distribution. So you have to be, you have to be very, again, sometimes I swear AP statistics is detail oriented and paying attention to what we get written down. Okay, so notice the difference here. Up here in this calculation, we had the standard deviation of my the mean and standard deviation of a population. Where down here, it's of a sampling distribution, so we have to put x bar on there. Okay, but because of my central limit, and we haven't got to the central limit theorem yet. Did we blow by that in the notes? Was that even in the notes? Okay, the central limit theorem says that that's basically this here. Okay, the mean of my population is going to equal the mean of my sampling distribution. All righty, let's move on to another example. The distribution of heights for 6A high school basketball players in Kansas is skewed right with a mean of 69.5. So that means with a standard deviation of 3.5. And again, it is skewed right because we're going to have a lot of players probably in the 5'10 to 6'2 range, but then we're going to have that smattering of players that are 6'5, 6'8. I don't know if there's any, 7-foot players in the state of Kansas or not. But again, we're going to have those few really tall kids out to the right. Anyway, so here we go. All right, I haven't done a very good job of watching the chat room. It appears to be we have no questions, so I hope we're grasping this. The distribution of heights. Again, I already read the question, so that's irrelevant, Ted. Here we go. Find the probability the randomly selected player is taller than 72 inches. Okay. I don't want the highlighter. So again, if we go through the process, it's a probability. So the probability that x being greater than 72. If we draw that out, we have our mean, we have our middle marked at 69.5. We're talking about a 72-inch player. So there's 72. Something seems amiss. A 6-foot player is 72 inches, isn't it? Yeah, I don't think that's probably the case came from the Department of Made Up Data, I'm sure. Which most everything in this packet is. It's more about the principles that we understand. All right. Where was I at here? I'm trying to pay attention to emails and everything. We're going to go into a z-score. And again, it's so we are observing a 72-inch individual. We're expecting the individual to be 69.5. The standard deviation was 3.5. And so that gave me a 0.714. Now, if we this is the one we have to pay attention to. This is a right-hand tail, so when I look this number up, I get a 7611, but I have to remember we're going to subtract this from 1 in order to make that happen. So that's going to be 0.2389. Now, if we go back to the picky part of things, I have identified a variable x. But nowhere in my problem does the problem state what x is. So this would be a case of I need to write in there x equals the height of 6A b-ball player. And again, you had to note that we have this as a normal CDF. We can do that. Now, I'll ask this and see. I did a normal calculation here. Was I permitted to do a normal calculation here? What issue do we have here? I just started going on a normal calculation. However, in reality, I should not have done a normal calculation here. I did not have the grounds to do that. It had to do with the shape of my population. What does it tell me about the shape of my population?
It's skewed right.
It is skewed right. There it is. So that means that I actually, and the AP exam is not going to try to trick you. However, because the population is skewed right, we are going to proceed with caution. Okay, so that again, that's just something to keep in mind as we do that. Always, if we're doing a if we're doing some type of normal calculation, what we're doing a normal calculation on needs to be roughly approximately symmetric in order for that to happen. All right. So in part B, we're going to take a simple random sample of 35 high school basketball players. Will the sampling distribution be approximately normal? Okay. So now we have to know our why. Why am I going to say yes here? What characteristic about my sample is allowing me to do a normal calculation? Anybody? So again, we're going to go back to
The
here.
sample is larger than 30.
There we go. We have these are the three criteria that we have to meet in order to make the sample. In this case, my sample size is greater than 30. Okay. So yes, because sample size is greater than 30. All right. So we're ready to do another one. So find the probability that the mean height of the simple random sample of 35 high school players is less than 68. Oh, fine. Make me draw a new curve. So again, even though it's a sampling distribution now, I'm expecting the center of my sampling distribution to be the same as the center of my population. That part didn't change. However, on this particular problem, we're going left of 68. Okay. So we're going to go z is equal to, the observed value is 68. The expected value is 69.5. However, this is the part that I had to pay attention to. And on the previous problem, I made it its own separate calculation out to the side. So I just stuck my new number here and ran. Typically, I would divide by my standard deviation, and my standard deviation is 3.5. But we have to remember, because I'm dealing with a sampling distribution, I have to adjust my standard deviation because the variability decreases. And now this becomes a square root of 35 underneath that. Okay. So again, make sure I will highlight this. This is the part that's different. Okay. I have to make that adjustment for my standard deviation when I'm dealing with a sample. So this is going to be negative 2.54, which if I look that up in a table is going to give me a 0.0055. And again, that's a normal CDF. Negative infinity to 68 to 69.5 And again, I'll just write in 3.5 divided by the square root of 35. There we go. All right, so this is my lower boundary, this is my upper boundary, this is my sampling distribution mean and my standard deviation of the sampling distribution. Okay, so just remember that. All right, example 4, the length of the human pregnancy varies according to a normal distribution with a mean of 266 and a standard deviation of 16 days. So we go ahead and define that variable. I noticed it wasn't defined, so x is going to be the length of pregnancy. So we are officially in the Department of Redundancy. These examples all work the same exact way. There's 3 examples of the same thing, but we'll just make sure that we're trying to get the concept down. Find the probability that randomly selected pregnancy randomly selected pregnancy lasts for more than 270 days. So nothing new here. Okay. What? But now, sorry, I'm getting distracted here. It actually varies according to a normal distribution. So because it told me that, we can do this. If it hadn't have told me that, I was going to be out of luck. So greater than 270. So we expect a pregnancy to last 266 days, which how many of them last more than 270 days is what I'm trying to figure out. So again, I'll do that z-score thing. 270 minus, I'm expecting it to last 266, but we have a standard deviation of 16 days. Okay, that's going to give me a 0.25, which is going to give me a 0.5987, but then I have to do 1 minus 0.5987, and that's going to give me a 0.4013. And again, if we want to, I'll write it in here. I'm not sure I'm right. Well, I'm writing it in here for those note takers afterwards, but let's see. My 270 is my left boundary. Infinity is my right boundary. Um, man, all of a sudden I brain lapse. There it is. Lower boundary, upper boundary, mean, standard deviation. So remember, just as another thing, if by using the formula, that replaces identifying the variables. Okay, because we have used a formula, we have to understand what the variables are. So that's the rationale between that. So that's why we had to label, put our calculator speak here, versus if we use the formula, we don't have to do that. And in reality, sorry, this was laid. Mean was defined here. Standard deviation was defined here. So in reality wise, this would be unnecessary for your final answer. However, it's just good practice to do that. Will a random sample of size of 6 women have approximately normal distribution? So I'm running into an issue. My sample size is very small. It's 6. Okay, so I'm not meeting that greater than 30 criteria. So the criteria that we get to meet on this one is already highlighted, and it is an approximately normal. My answer is going to be yes, because population, oh my God, is normal. Find the probability that the mean pregnancy, find the probability the mean pregnancy length for a random sample of 6 women exceeds 270. So this one was nice to us. We get to say you're going to use the same picture. All right, that works. Same probability statement. However, my z is going to change because we're still going to do 270 minus 266. However, we have to, because again, it is a sample of size 6. We have to adjust my standard deviation. It was 16, but now we're going to divide that by the square root of 6. So we get a new standard deviation. And again, on the very first one I did that its own separate calculation. I just pulled it out, but we can just put it in the equation. Sorry. Got a burp. Okay. So I don't know. I don't know if you need to actually hear me do the calculations. So I won't talk through the calculations. I'll just write them down. So there we go. And this is one of those drudgeries as far as if we were doing on our usual schedule, this would be where I'd be stopping because I'm done. However, since this is blocked now, um, we got to cover some more. So this is the mean of my sampling distribution, and then 16 divided by the square root of 6 is going to be the standard deviation of my sampling distribution. All right. Oh, there we go. All right, moving on. Because what happens is now we can work with materials and we can work with data as far as one sample go, but we can also work with data with two samples. So in a two sample, this is going to be like, is there a difference between you know height? I want to say heights of basketball players, male and female, but that's clearly obvious. I want to see let's say reaction time, and I use my dominant hand versus my non-dominant hand, and I want to see, is there a difference between the two? Well, and that's what I will do. Then I will find the mean for my right hand and the mean for my left hand. And if there is no difference, then I would expect a difference of zero. However, if there is a difference between my reaction times when I subtract those, and I did a horrible job probably explaining that, but hopefully we'll get that as we get into the next example. Okay, so what we're looking at here is this is from our parent population. So now what we had to pay attention to is I'm going to have X bar 1 and X bar 2. So I'm going to have two sample statistics, and I'm going to have a sample size 1 and a sample size 2. So this requires a little bit more notation, I suppose to speak. Anyway, so the mean of X minus Y is going to equal the mean of X minus the mean of Y. And typically I'm going to expect that to be 0. Okay. So, um, other ways to write that. Um, looking at my notes. Um, we could write that if we wanted to, which means mean of X bar 1 minus the mean of X bar 2. Again, this is just notation wise. When we get into notation, we could also just do the mean of 1 minus the mean of 2. But what happens is we have to define 1 is the, 2 is the. Okay, so this is where it gets into this, again, being attention to detail. We have to go ahead and define what all those are. Okay, now standard deviation. How are we going to combine two groups as far as standard deviation? So we have to remember how do I if I was talking about so I'm going to come up here, the standard deviation of X bar 1 minus X bar 2. So I'm going to put two groups together. So this goes back to we did a little bit of it last chapter when we had there was a test question on the multiple choice final where we oh my gosh, what was it? It was the movie player question. Um, the mean was 10 and the standard deviation was some number. And so we had to remember how that works as far as when I'm putting groups together. Um, Remember that if I'm talking about the standard deviation of 1 and 2, that means that I'm going to have to take the standard deviation of group 1 and square that, and I'm going to have to add to that the standard deviation of group 2 and do that, and then I'm going to have to square root it. Okay? Now, the problem is I'm dealing with samples. So in adjusting for samples, I have to remember that I'm going to have to divide by n and divide by n. So that's what my standard deviation calculation now becomes, is it becomes the standard deviation squared of 1 divided by n1 plus the standard deviation squared of 2 divided by n2. And I probably did an absolutely craptastic job of explaining that. So we'll jump out of this real fast. I will get back to it. We'll go to my formula sheet. And if I look at the formula sheet, now we're talking about for two populations. My mean is going to be the mean of my sample is going to be the mean of my population. The mean difference of my sample should be the same as the mean difference of my population, but we can see over here that now my standard deviation becomes a little bit more convoluted But that's generally why, what I tried to do beforehand was trying to be a brief explanation of why we're dividing by the square root of n. Again, where we're going to square it to get to variances, but we have to divide by n for that adjustment. And now I need to get back to our notes key. Alrighty. Normality. Oh, can be let's see. So as long as we got a couple of different things that are kind of stuck in here. I didn't do a very good job of spacing this out. Um, we can do this as long as we are independent. So independent means my sample size doesn't get too large, and that, remember, is n is less than 10% of n. So that kind of just snuck in there as far as long as they are independent, then this is true. Okay. And then step 3 of this is approximately normal can be assumed with the same rules as above, but we'll put in here one sample. So the difference is that I'm moving from one sample to two samples is the difference. Okay. A man who lives moves to a new city sees that there are two routes that he could take to work. A neighbor who lived there a long time tells him route A will average 5 minutes then route B will average 5 minutes faster than route B. The man decides to experiment. Each day he flips a coin to determine which way to drive, driving each route 20 days. He finds that route A takes an average of 40 minutes with a standard deviation of 3. Route B takes an average of 43 minutes with a standard deviation of 2. Histograms of travel times for the routes are roughly symmetric and show no outliers. Alrighty. So identify the statistics of the sampling distribution of the different routes. Okay, so in this case, this is a this is a little bit different as far as the statistics. Statistics again come from a sample. So we have a sample of 20. We drove each route to 20 days. So we have those samples of 20 out of all the times we could possibly drive that. So let's identify what we have. Okay, so we have route A. We have X bar of route A. So that means this is the sample mean of route A. That's going to be 40 minutes. And we have a standard deviation of route A. And that's going to be 3 minutes. We also have the mean. And again, you can use different things in the notation. It could be the mean of X bar 1, or we could have established that 1 was route 1 and 2 was route A and route B. I'm crossing things over. That's some of the problems you can get, especially with me grading. Yeah, I guess I see so many variations of notation, but there's really no way around that. Anyway, here we go. All right. Now the thing is, and the hard part here is we need to have a mean and a standard deviation to do the normal calculation. So we need to have a mean of A minus B. So we need to know, is there a difference in these routes? So that means this is going to be the mean of A minus the mean of B. So we're going to have a 40 minus 43. So that gives me a -3. So this curve. If I looked at the different, if I paired those up and I subtracted them, I would get an average of -3. The standard deviation of A minus B. We're going to have 3 squared over 20 plus 2 squared over 20. Because the n, oops, not what I wanted to draw. The number in A was 20, and the number of B was 20. Anyway, we're going to get a 0.806. All right. The question is, will sampling distribution of route A minus route B be approximately normal? And again, there's a reason for that was in here. Histograms are roughly symmetric and show no outliers. Okay, so because of that, yes, because both samples had roughly symmetric box plots with no outliers. Okay. So, C, what is the likelihood that route A is 5 or more minutes faster? Okay. So, we're going to find a variable. D is going to be the difference between route A and route B. So, if route A is faster and we want it to be 5 minutes faster, my probability is going to be what is the likelihood that that difference is less than -5? Okay, so for example, let's say one was 40 minutes and if A was 40, that means B would have to be 45. And so that means that we would expect a difference of -5. So that's what we're looking for. We already know from the statistics that we did was it is 3 minute difference between the two because if we look, our neighbor, and the reason we chose 5 was our neighbor said it will be 5 minutes faster. So that's what we're doing here. Okay. So what is the likelihood that it is 5 minutes or less faster? So out here is -5, and we're trying to know what portion, based upon my samples, how often would we see a difference of -5? So we're at -5 minus a -3 divided by my standard deviation of my combined samples is 0.806. And so we're going to get a -2.48. And that means that we're going to get a 0.006. So, based upon our data, we can tell our neighbor he's full of it because we got a probability. It's very, 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 very unlikely that we would see a difference of 5 minutes. So again, I wrote down, I'm going through there, I wrote down mean of X bar, but that's not the mean of X bar. I defined what X bar was, the mean difference, standard deviation of difference. There we go. Ah, man, today's a killer. Information overload, not information overload. Kind of been doing the same repetitive stuff the whole time. Man, that's why it's a killer. Okay, let's scroll down here and see what we got. Oh, well, there's proportions right there. So that means we only have this one more to go. So here we go. Example 6, a researcher wanted to see if there's a significant difference in the resting pulse rates of men and women. She collected and displayed the box plots, and the box plots are summarized below. Identify the statistics of the sampling distribution of the difference between men and women. Okay, again, these are going to be. This is kind of weird. It's not a population because it's not all men and women, so that's why it's a statistic. It's going to be a sample. Okay, so and just to shorten this up a little bit, we're going to let this be the mean of men, and this will be the mean of females. Okay, we're going to have the I don't know. This will be the standard deviation of men, and this is going to be my standard deviation of females. Okay. Now, typically, again, sometimes I struggle with my notation. These are all samples, so that means they should all have bars over them. All right, but there we go. So what it actually, it wants to know, we want to find the difference between men and women. So that means I need to find a mean for males minus females. So I could do many things. I could say D equals the difference of male and female. And that means I could come down here and I could really be talking about the mean difference, or I can write it out as M and F for male and female. So it's however you want to roll with that. You just need to figure out what you like to do. Anyway, that's going to be the mean of male minus the mean of female. And if we do that, that's going to be 72.75 minus 72.625. And we're going to get a mean difference of 0.125 beats per minute. Okay. We need a standard deviation of male minus female. Unfortunately, I'm going to have to cram this because I've really, but we'll live. So that means we're going to have, and of course, these are long numbers. We're going to have 5.37225 squared divided by 28 plus 7.69987 squared, and we're going to divide that by 24. And that turns out to be 1.87 beats. Will the sampling distribution of the difference between genders be approximately normal? And again, you got to go back to your rules. Your rules are if my populations are normally distributed to start with, I'm okay. Well, that's not the case here. If my sample sizes are greater than 30, I would be okay. Well, that's not the case here. So because we're actually picked data, then that's why we have to have the box plots here. Yes, because box plots are roughly symmetric. What is the likelihood male pulse rates are faster than female pulse rates? So what is the likelihood that that difference that we found, that males minus females, is going to be greater than 0? And again, if we had defined D, we defined D up above, so we could have said D instead. It's whatever, again, however you want to note that. So again, from part A, we found that we would expect there to be a 0.125 difference between the two. We want to know what is the likelihood of, here is 0, and we want to know, is there a difference? So greater than 0. So there's probably a high probability of that happening. So we'll see how high that is. So we're going to convert that to a z-score. So we have the observed is 0. We're going to expect that difference to be 125. And my standard deviation is going to be that 1.87 that we pull in there from above. So that means we get a negative 0.067, which we can convert into 0.4721. But because it's a right-hand tail, we have to subtract that from 1. And that means that we're going to have a 5279. All right, so there we have it. We've gotten to the a couple of two sample examples as far as when we do the difference, and we have hit the sampling distribution for one sample. So proportion. So we don't have to go. We just needed to proportions is next week. So I'm going to stop the recording.